Hello, this is a lecture on vibration signal analysis for 48601 Mechanical Vibration and Measurement. My name is Dr. Benjamin John Holcomb. I'm Senior Lecturer here in Mechanical and Mechatronic Engineering at Faculty of Engineering and IT at UTS. In this lecture we will follow on from a previous lecture where we introduced concept of vibrations measurement, essentially looked at sensors acquisition, sampling, some of these theories, and extend that into the analysis of vibration signals, particularly aiming towards structural testing, which is the topic of one of the forthcoming laboratory activities that will be undertaken by students on the program. We'll introduce some additional vibration sensors, in this case specifically for rotating systems analysis, or primarily for rotating systems analysis, and this will be a subsequent laboratory exercise that will happen towards the end of the subject. I'll introduce aspects around measurement uncertainty, how to optimize a signal quality and how that impacts on the signal analysis. We'll also talk about the ways that we can present vibration levels, look at some example standards and some example activities finally that have been undertaken here at UTS in previous years. So in terms of a recap on measuring vibration, in the introduction we looked at why we choose to measure vibration and which is the principal parameter of interest to measure. We explained the differences between measurement of displacement, of velocity and acceleration, and identified the fact that the velocity parameter was the optimum to measure in a vibration scenario when we're interested in frequency ranges of interest that are relevant to human beings, so between 20 Hz and 20 kHz. We looked at various different examples of transducers for all three parameters in terms of types of measurements: displacement, velocity and acceleration transducers, compared and contrasted them, and then we went on to subsequently explore the differences between those in one of the laboratory exercises at the start of the session. We talked about calibration of sensors. We introduced the concept of the vibrometer calibrator, the use of a vibrometer, laser vibrometer as a calibrator. We also talked about the handheld calibrator, and you had a chance to use this in one of the laboratory exercises. We went on to talk about frequency response. We looked at different types of analysis, initially at least in terms of amplitude and in terms of frequency domain, so using Fourier analysis. So that recaps what was studied, and if you have any thoughts on what we did previously, then I recommend you go back and have another look at that video that I recorded at the time for that session. From an additional vibration analysis standpoint in this particular lecture, then I want to begin to introduce concepts around octave or constant percentage bandwidth analysis. So in this case you'll notice that on this axis, the frequency axis, we're using a logarithmic scale. We've already looked at the use of a logarithmic scale on the amplitude axis. In fact, in this case we're not using, indeed we are, using a decibel. This is in decibels, it's not got the units identified here. It looks like a linear scale, but of course the decibel is a logarithmic measurement or a logarithmic scale. So this is log essentially, and you can see that the distance between the points essentially is greater at the lower frequencies, where the distance between those data points, we've got 1 to 10 within the same. So this is a 9 Hz band essentially, and then this is a 90 Hz band, and then a 400 Hz band at this end. So clearly the distance between the points is much smaller at the upper frequency range than it is at the lower frequency range. An alternative way to present these data, and these are exactly the same data presented in this block looking chart below, which is a constant percentage or octave band analysis presentation. So we effectively consider the energy within this particular band from this range of frequencies within our frequency spectrum. So you can see unsurprisingly, there's lots of energy in this region here because it's dominated by this peak. Similarly over here, there's a large peak here, but the area around it is relatively low level, so while the peak is somewhat high, it's not as high as this peak. And indeed here we have a higher peak in terms of constant percentage bandwidth because we're essentially capturing all of this energy. And remember, there's more frequency lines in this region here than there is in this region here, so this is more densely packed, and therefore there's more energy in this particular octave band. Octave band analysis or constant percentage bandwidth analysis is used, for example, for kurtosis analysis, where we use kurtograms in machine vibration analysis, where we want to compare an existing frequency spectrum with a previously recorded frequency spectrum because we want to understand if the machine is performing within the vibration frequency limits. And it's much easier to do that with an octave band scale than it is to do that with a full 500 or 5,000 line frequency spectrum. We can set up some rules very clearly comparing different octave band levels with one another, and we can easily say this machine passes the health test or this machine fails the health test. And another area where we use constant percentage bandwidth frequency spectra is in acoustic measurements, because the human ear responds to different tones in a logarithmic fashion. So we have particularly good hearing around the 50 to say a kilohertz band. Beyond there, we're not as able to differentiate frequencies that are say 50 hertz apart from one another as we are when they're within the lower frequency range. So our hearing responds in a logarithmic fashion too. So we often present acoustic data on this similar axis system. We looked previously at logarithmic amplitude scaling. We didn't perhaps really explain fully the nature of logarithmic amplitude scaling. So here you can see the same data again, albeit simulated data, presented on a linear axis on the left hand side and a logarithmic axis on the right hand side. Note that the logarithmic axis doesn't start from 0. It has to have a finite value from which it starts from, unlike the linear axis, which clearly can start from 0. What we effectively achieve with a logarithmic scale is that we amplify the significance in terms of how the peaks are perceived of the smaller or the lower peak levels. And this is important because when we do vibration analysis, we're interested in all the frequencies and all the levels within the entire frequency range, even if they're small, because if it's the case that presently this measurement they happen to be small, if we excite the structure, and let's take for example the case of a frequency response function, which is a response output divided by a forcing input signal, which I talked about in my week 6 lecture, I think it was. If we excite a structure at a resonant frequency, then clearly all of a sudden we have lots of response. So even low frequency or low amplitude peaks in a frequency response function are important, because if the excitation coincides with them, then we get lots of amplitude of vibration, and that's why we use a logarithmic scale on the linear axis to present vibration data. Talking about windowing for acquiring these chunks of time or blocks of time that are used to calculate the individual frequency response functions. Typically we will collect a number of frequency response functions because we want to make a series of averages to get our frequency saying frequency response function, but it equally could be a frequency spectrum. So we'll measure over a certain amount of time, and if you can see on the left hand side we have in this case a single sinusoidal component with a single peak, as we would expect in the frequency spectrum. The FFT that we make to convert from this block of time data, in fact it's this block of time data in the middle, assumes that the input signal is periodic about t, i.e. what that means is that if we were to take an inverse Fourier transform from the frequency spectrum, we would expect a sinusoidal signal that would continue indefinitely, as is shown by this signal in the top window. And the key here is that there are an integer number of periods within that time window. In this case there is actually 2.5 periods in that time window. So in this instance here we wouldn't, so this is our input time signal, this is our expected Fourier transform. Actually what we get in terms of Fourier transform, because the FFT assumes that this repeats, is that we get a discontinuity at either end, because this is not an integer number of cycles within the time period, it's 2.5 cycles. So we start again here, and this is the shape of our reconstructed time signal. This constitutes leakage in the spectrum. So in addition to the peak at the frequency, the correct frequency, we have leaked signal content either side of that, and that's undesirable. That, for example, amplifies what we might consider to be damping, and this is just a mathematical relationship now between this signal, the frequency representation, and the time representation. So this is undesirable. How we achieve or we overcome that when we're dealing with arbitrary signals that we measure from real structures where there's no guarantee that the number of periods fits nicely within our acquired time window, is we multiply by a window function. Typically we would use a Hanning window function. There are other forms of window function including flat top, Kaiser-Bessel and other various functions that are used for specific cases, but if in doubt we use a Hanning window which multiplies the content at the start of the time block by 0. At the middle of the time block we multiply by 1, so we actually get the full signal level coming through, and then at the end we taper off again to 0. So we eliminate in our reconstituted time signal these discontinuities at each end of the time window, and that minimizes leakage within our window, within our frequency spectrum. Here again, as I mentioned previously, there are various different window types. So we have a concept of a rectangular window, but it's essentially no window at all. We just multiply the entire time block of data by a value of 1. The Hanning window is shown in red. The flat top is shown in blue. The flat top doesn't relate to the shape of the window within the time domain, but the shape of the frequency peak that we get within the frequency domain. So a flat top gives us essentially in the frequency domain a flat top. So our frequency spectrum, when we have a random signal with a frequency that's unknown, doesn't fit exactly onto one of our frequency lines of interest. A flat top basically means that the peak level of the spectrum, the spectral peak, is shared across 2 or more adjacent frequency bands. Then we've got this concept of an impulse window. This is used for when we use, for example, hammer excitation, and we want to reject noise that occurs towards the end of the time window because we're really only interested in what happens up front. Similarly with the response of the structure, when we do hammer excitation, it's a decayed exponential, and by the end of the window all we've got left is noise, and we want to minimize that noise to 0, so we use this kind of an exponential, negative exponential shape as one of our window options. We also need to do averaging because we want to maximize the signal to noise ratio in our output data, and there's a noise in every experimental signal that we might acquire, and so the noise, typically the non-deterministic signal noise, if we average enough frequency spectra together, so we capture enough blocks of time data and average them together, we reject the noise. If we average a random number enough times, then the result is 0. So that's essentially the concept of using linear averaging. There are other types of averaging, including peak hold averaging, where we collect for each of the frequency lines within our spectrum the maximum level in each line, each spectral line, or exponential windowing, exponential averaging, where we increase the relative importance of the first averages within our, say, 10 averages, and give less significance to the later averages within our average block. So these types of averaging are mentioned in here. We've got spectral averaging, which we would do on an RMS power, and we're using averages to reject noise, and if we have overlap between our different blocks of time data, we can, because we're using the Hanning window, which has got this shape to it, which is a curve, we have less significance for the bits at either end of the time window. So we can actually, from our continuous block of time data, take our time blocks with some overlap, such that we give the same importance to each of the individual blocks of time data that are used to calculate each of the individual spectra that are then averaged to give us our average auto power spectrum. In the lecture there would be a demo at this point. I've mentioned that we are particularly interested in vibration testing of structures, impulse testing, so we use an instrumented hammer. The hammer is instrumented with a force transducer. We've not yet looked at force transducers. We introduced them previously. Essentially a force transducer is an accelerometer but without the seismic mass, so we just have the piezoelectric element, and when we apply a force onto a structure, and this would be a fast changing force, not a load. It's not a load cell. It's important to differentiate between a force transducer and a load cell. A load cell measures a static force. This is a dynamic force, so we refer to this transducer as a force transducer. We measure the force transducer, we measure the response, and we divide the response by the excitation signal which we get from the force transducer. I've shown the concept of structural analysis in my previous session in week 6. This is the frequency response function that we acquire, and we can see there's multiple resonances within that. Each of those essentially can be considered to be a single degree of freedom system. If we were to do a zoom analysis on just one of the particular peaks of interest in here, we can estimate the damping by considering the half power. So 3D, remember, a 3 dB reduction is half, and we consider the width of the peak at half power. That gives as an estimate of the damping in that signal. So a nice sharp peak is a lightly damped structure, a wider peak is a more highly damped structure. So this is one means by which we do impact testing. We need to excite the structure, we have to consider the nature of the impulse that we use using our impact hammer. If we have a large structure, we use a large impact mass. For lighter structures, we use a lighter impact mass. And these are pretty good for readily and quickly identifying modal frequencies. And you'll get some experience with this in the laboratory. When you don't know anything about your structure, you can very quickly get an accelerometer, take a hammer, excite the structure at a series of different locations, collect a series of FRFs, and extract mode shapes from it, and we'll be doing that in the exercise that we do in the laboratory. In terms of how much excitation we get over what frequency range, that is a function of the duration of the impulse, and the duration of the impulse, of course, is a function of the stiffness of the tip of the hammer. The stiffer the tip of the hammer, the shorter the duration of the impulse. We also have to consider the stiffness of the structure itself. If we've got a very soft structure, then clearly that will also lead to an extended duration. The longer the duration, the shorter the excitation frequency range. And our useful range we typically consider to be 10 to 20 dB down, so a factor of 100 for 10 dB down from the peak force level. So this is our useful frequency range from 0 Hz to F. This repeat here occurs at 1 over the period of the impulse, and then there's another bounce, and so on and so on. This is on a log scale, and we can see this in experimental data quite readily. So if we want to excite over a wider frequency range, we need to shorten this pulse. And how do we determine the frequency range of interest? Well, we need to have some knowledge of our structure. So if our structure is very stiff, then it's likely to have very high natural frequencies. If we're only concerned with the first or second natural frequency, then we can specify over what frequency range we need to do our excitation to extract information about those natural frequencies. If our structure is less stiff, it will have a series of natural frequencies at lower levels in frequency range, and we can potentially make our tip stiffness less to excite over a shorter frequency range. So that's how we determine, and we either determine where our structural resonances are by doing some kind of pretest, or we can potentially have a numerical model. So a finite element model might give us an indication as to where our frequencies are for the structure of interest. So our instrumented hammer looks like this. We've got essentially a force. This is our structure shown here with a hashed line. We strike the structure at this particular location. It's important to maintain the impact location and the impact direction. These things will affect the quality of the result. So we have a mass associated here with the tip, mass of the hammer. We can potentially introduce some extra mass. We've got a total mass then that is the function given by this. We can have a force transducer here which is connected via a cable into our acquisition system, and below here in this graph you can see that we typically can increase our time excitation duration by softening the tip, so going from steel through plastic into rubber, and the corresponding frequency excitation is shown over here. So as well as having some impact on frequency range with the stiffness, i.e. changing from rubber to plastic to steel, so increasing stiffness gives us greater frequency range. We can actually also add some mass. So the mass, of course, changes the duration of the impact. More mass gives us actually greater degree of excitation. Accelerometer mounting is also very important. We've got various options for that, and they've got various different eases of use. The reason it's important is because the mounting arrangement effectively is a function or determines the frequency response of the accelerometer. So the stiffer the mounting, the higher our frequency range over which we can make measurements. So for a steel stud, which is very stiff, we get a useful range for our accelerometer, which remember is a single degree of freedom system over a wide range. But it's a bit difficult to use because we have to drill and tap our structure, which we may not want to do. We have to insert the stud, then we have to screw the accelerometer onto the stud, and so from an ease of use standpoint it only gets one tick. Beeswax or synthetic beeswax, which is more commonly used nowadays, is essentially just like that's like candle wax, but it's a little bit more manipulable or malleable at room temperature, and we can use that to just effectively get a very thin film of beeswax between our accelerometer and our structure, and that gives us a very convenient, quick way to attach an accelerometer. It's not good, of course, for high temperatures because wax melts. So if we're connecting to an exhaust system or something within an engine or an aero engine or factory processing line or anything where we've got some temperature, then that's not a good scenario. We can use alternatively cement, for example. We can cement a stud onto a structure. We can use thin tape between the accelerometer and the structure, so that's a similar performance to beeswax. The more material we have between our transducer and our structure, then the more we have a little bit of a mass spring situation. So we effectively introduce an additional spring, and you can see that when we use thick tape we really significantly reduce our useful frequency range. We can also use a mag mount, which would have a stud. Our accelerometer is mounted to a magnet, and for a ferric material or ferric structure like some sort of structure that might be used in a bridge or on a vehicle, perhaps subframe for example, that would be in steel rather than in aluminium, then we can readily move the magnet mount around the structure. And so you can see that this is a compromise between ease of use and high temperature, so there are some options in terms of alternative frequency range of interest. So those are the three compromises. We also need to consider mass loading effects when we use accelerometers to make measurements from structures of interest. If the relative mass of the accelerometer is large compared with that of the structure, then of course the mass will change the characteristics, the dynamic characteristics of the structure. So it's desirable to reduce the mass of the accelerometer, or for example we use a laser Doppler vibrometer, which is non-contact and then therefore applies no mass. We can also, if we're using some accelerometers, actually subtract the mass. So when we have our modal model in software from these experimental data, we can subtract an equivalent amount of mass if we really are interested to estimate what would be our true structural resonance performance or dynamic characteristics. Without the accelerometers attached, we can extract them. We can subtract them from the mathematical model that we create from the experimental data. And that's the point of the exercises, that we're using these experimental data to build a mathematical model which we can use to either make some modifications to quickly in the mathematical model or correlate our finite element model and make our modifications to the finite element model. So we always need to bear in mind what is the point of the exercise, and it's those things. We can also, in addition to force impact hammers, use shakers. So electrodynamic shakers, as are shown here, typically used when we want to get lots of averages, for example. So if we want 20 averages because we need to really maximize our signal to noise ratio, then doing that with a hammer is tricky. For one thing, it's very difficult to strike the structure in the same location and in the same direction 20 times exactly the same. It doesn't matter if we hit it slightly harder or slightly less, because remember, we're taking a frequency response function, we're dividing by the force measurement all the time. So if we use less force, our system transfer matrix is a constant, so our response, we get less response for less force, and then the transfer function is the same. However, if we want to collect lots of averages very quickly, or for example we have a structure where we have lots of accelerometers, we can populate the entire structure with accelerometers to collect the response data, or we have a laser vibrometer, a scanning laser vibrometer, where we want to be able to move this laser beam around on the structure rapidly, then a shaker is a convenient way to excite the structure, and we can very quickly collect a lot of experimental data and do a very, very detailed survey on a complex structure. Typically we would still do a pre-test with a hammer excitation to understand where the natural frequencies are, so we know what the frequency range of excitation is to excite, say, the first 10 natural frequencies, because we need to provide the shaker with a broadband noise signal over the frequency range of interest. So we use a white noise signal to power the shaker, which is effectively like a speaker. It connects to an amplifier, and that amplifier is provided with a signal from our data acquisition system that is of a broadband white noise in characteristics. As it says here, we can use a swept sign if we want really fine resolution in our spectrum, but other signals such as white noise and chirp and burst sign can be used, or burst random in fact can be used for identifying mode shapes for large structures, again with lots of damping, but we need to take care that the shaker does not become part of the structure, i.e. adds mass, stiffness and damping. We can also use multiple shakers. We can do what's referred to as multiple input, multiple output testing with multiple shakers attached at different locations, perhaps exciting the structure in different orientations, particularly important for 3D structures, large structures like satellites or automotive vehicles or aircraft. You can see lots of videos on the internet of large shaker campaigns, test campaigns, where multiple shakers are being used to excite a large complex structure. At this point in the lecture there would be a demo. We need to introduce now some additional vibration sensors. So magnetostrictive transducers are a vibration sensor of use. These ones you've seen, you've been hopefully able to observe these. These are good for measuring displacement. They're non-contact. There's no wear. They're pretty rugged, good for use in hostile environments. And these ones were the types of sensors that we used in the remote labs experiment that you were able to collect some data from previously in the subject. They're good for frequencies up to several hundred hertz, not very good for frequencies up to the order of kilohertz. Proximity probes are useful to be able to make measurements from rotating structures particularly. They're used for example, looking at shaft orbit measurements, to collect pulse trains from geared wheels, for example, as the gear moves, or the tip of the tooth of the gear moves past the sensor. Then the magnetic sensor, the field, provides or generates a pulse which can be measured in an acquisition system. They've got to be used pretty close to the target, less than 5 millimeters, so they're quite good for small displacements, but they're also sensitive to shaft runout. If we're using them to make measurements of rotating shaft orbit, any runout on our shaft would also be measured as part of that orbit, so we can't differentiate orbit from runout in a shaft measurement. What sometimes we would do to do that is just do a very slow rotation of our shaft, and we can use that to get a baseline for the runout, and then we can subtract that from the measured signal that we would obtain at high speed. Here's an example of a shaft orbit measurement, runout measurement. So you can see here that we've got 3 proximity probes in different locations around this shaft, and this shaft is orbiting, the center of the shaft is orbiting around on this profile here from 1 to 2 to 3 to 4 to 5, and so you can imagine that these sensors will measure the orbit as the shaft moves towards them and away from them at different locations during the rotation. Torsional vibration measurements, powertrain applications. So we use various different transducers in these scenarios, including torque transducers, which I'll introduce more shortly, strain gauges, surface acoustic wave sensors. For all of these sensors that are connected to shafts, we require some telemetry or slip rings to be able to extract the signals from the shaft if it's continuously rotating. If it's a reciprocating shaft moving backwards and forwards, which it might be, for example, in a production scenario, then we might be able to just have enough cable to be able to get the sensor measurement into the acquisition system. But for constantly rotating, clearly we need to pass those cables into a slip ring and extract them from a non-rotating part, and that introduces noise into the measurement, so it's non-desirable typically. What we could use as an alternative, and you'll have some exposure to this instrument later in the subject, is a dual parallel beam laser vibrometer, which is particularly well suited for torsional vibration measurements from rotating shaft systems. It's inherently insensitive to shaft shape variations, so unlike the eddy current probe that I mentioned previously, which is sensitive to runout, the parallel beam laser vibrometer is not sensitive to runout, to shaft shape variations. You can make measurements from circular wheels, square wheels, toothed wheels, cams, and all you will measure is the torsional vibration. It's not sensitive either to radial vibration measurements, so translational vibration measurements, because each beam measures the same component and it's a difference measurement that's made with a dual parallel beam laser vibrometer. In terms of the torque transducer, these are typically bolted into the shaft system, so we would bolt one end of the torque transducer, perhaps there would be a clamp around here and another clamp here. It would be a flexible coupling between the torque transducer at either end and the shaft system. Of course, it changes the driveline torsional stiffness and the inertia, because we're adding in the inertia of the shaft system. We introduce these flexible couplings. We will inevitably have misalignment, so that's why we need flexible couplings in there. But it may be that this rotates, or maybe it doesn't rotate with the shaft, so we can extract the signals from it. In the case that it rotates, we then need some slip rings or inductive couplings to extract the signals onto the ground side, which is where we have our acquisition system. Non-contact torque transducers are an alternative technique that might be possible to be used. We have strain gauges attached to the rotating part with some degree of telemetry, some radio frequency telemetry between the rotating collar and the non-rotating collar. So there's this rotating element here provides power to the strain gauges and does signal conditioning, and then wirelessly transmits the data at relatively low frequencies to this base station, which is connected to the acquisition system. It's handy because it doesn't, it's not adding as much stiffness. Or indeed shaft stiffness to the system. It adds a small amount of inertia, but usually these shaft systems are relatively massive, so the change in inertia is negligible. I've mentioned previously the laser vibrometer. Here you can see an example of the RLV 55000 two-beam system from Polytech, which we have within Faculty of Engineering IT, and it relies on the Doppler shift due to target surface vibration to be able to make the measurement. This is a special type of LDV which is only sensitive to angular vibrations, which include torsional vibrations. It's non-contacting, therefore there's no mass stiffness loading, there's no need to worry about cabling, it's insensitive inherently to translational vibration components and shaft shape variations, as I mentioned. It is, however, sensitive to something known as speckle noise, which manifests itself as peaks within the frequency spectrum at order multiples of the rotation frequency. So if the vibrations of interest coincide with the orders of the rotation frequency, then speckle noise is not possible to be differentiated from them. Fortunately, it's typically fairly low level, but nevertheless it is an element of uncertainty in these measurement techniques. At this point there would be a demo. We have some measurement challenges to discuss with respect to cabling, for example, particularly in piezoelectric accelerometers. So it's important to keep our cables grounded. We have to be, well, when I say grounded, we have to avoid ground loops, so that we have to have the ground of the acquisition system connected to the same ground as the accelerometer system. So if we have an insulator in here, then that means that the ground is not going to be provided through here, and then we therefore need to connect ground across the cable. So what we want to avoid is a ground loop where we have two ground connections. So we want to only rely on one ground connection. Otherwise we can have a slight positive difference and we can get extra noise in the signal, which isn't good. We can particularly become sensitive to mains noise, which occurs at 50 Hz and integer multiples of 50 Hz. There are also triboelectric effects to be concerned about, so to be wary of. So if we're running large cable lengths, then we want to avoid those cables moving while the measurement is underway. So if we've got large structural vibrations and long lengths of cable, and those cables are not fastened down, then of course we can get vibration of the cables. Vibration of the cables, there's always a magnetic field present, even due to just the Earth's magnetic field, and that can generate a small amount of EMF. And that can add signal to our measurement, especially when we're dealing with very low level signals. Electromagnetic interference is clearly also problematic, so from other electrical machinery within the environment we can expect, if we don't have properly shielded cables, low noise cables, that noise, those changes in electromagnetic field can also induce electromagnetic changes within our measurement cables. Strain gauges are particularly sensitive to this. They need to be amplified very close, and there are 6-wire bridge configurations that are optimum over 4-wire configurations to assist in minimizing of electromagnetic fields. Some of the types of accelerometers are available. Current loop accelerometers, more typically used for condition monitoring of machinery rather than for modal analysis aspects. They're typically much heavier. They give outputs in proportional to current rather than proportional to voltage. They need to be provided with a current source, but they can also be used to output velocity as opposed to acceleration, which is helpful because we know velocity is our optimum measurement parameter. They can be used typically for manufacturing processes, so in manufacturing process lines, good for long cable runs, and they're AC coupled. Talking about signal concepts, we've mentioned previously this concept of noise that gets created by the transducer or picked up by the cables, voltages, earth loops. We can create noise indeed within the recording device itself. Typically, the more expensive the recording device, the less noise will be collected within the recording device. In terms of signal to noise ratio, this is a concept that's given again in terms of dB. We divide the signal by the noise, and it's important to maximize our signal to noise ratio. The dynamic range of our measurement system is the largest measurable signal divided by the smallest measurable signal, and again this is given in decibels. So typical decibels on the order of, for example, 80-90 dB for a 14-bit ADC, which is the system that we'll use in the laboratory experiments, but increasingly 16 and 24-bit ADC systems are available with 120 or 140 dB range. You pay a lot of money for them, but they are increasingly available, and they can clearly make much wider range of measurements, so much higher degrees of dynamic range. In terms of expression of vibration levels, then we can talk about concepts along the lines of the peak, i.e. the amplitude of the maximum level of the sinusoidal signal, which is useful for acceleration transients, so not talking about sinusoidal signals where we have a repeating signal that fluctuates either side of zero. If we've just got an impulsive event, it's useful to refer to the peak. Peak levels are also used to refer to sinusoidal signals, but more often we might refer to peak in a sinusoidal concept. So it could be that we have a non-zero midpoint, or some sort of DC offset, which might be half a volt, for example, and the signal fluctuates between 1.5 volts and half a volt. It's still going to be a 1 volt peak-to-peak signal, rather than, for example, trying to express its peak level in terms of 1.5 volts, because that doesn't take into account that it's got this offset on it. We can also use the root mean squared to talk about sinusoidal signals, and this is particularly important because if we talk about an average, then an average for a sinusoidal signal is essentially zero, especially if it fluctuates between -1 and 1. We average that signal over a long enough time duration and it averages out to zero. RMS, on the other hand, is given by the root mean squared. So we take the squares of all the data points, so we would have a squared signal. We would take the mean and then we would take the square root, and that gives us one value that for a sinusoidal signal is essentially the same as the peak value multiplied by root 2 over 2, or indeed the peak value divided by root 2. It's the same thing, so it's 71% of the peak level for a sinusoidal signal, the RMS. 1.414 divided by 2 is 0.707. Talking about vibration levels for typical machinery, then of course the RMS level becomes particularly useful. Peak level doesn't really tell us a great deal because we've got lots of energy happening and lots of vibration happening within this time duration, and the peak level really doesn't tell us much about the rest of the story, whereas the RMS level is particularly useful. Peak level can vary significantly. We might have one big peak one time window, and the next time window we have a different size peak, so those values can move wildly from one experiment to the next, one time window to the next. The RMS is much more steady, gives a much more statistically reliable measurement of the energy within the system. And we'll see the difference between the use of peak and RMS levels in the laboratory exercise that you will participate in week 12 of this subject. I've shown this figure before. This is about transient events, shock events, where time-based analysis is more important than frequency-based analysis. So we have these peak levels, for example, that decay rapidly, and we can integrate acceleration to look at shock, for example, and we can calculate, for example, head impact criteria, which are formulas based on the time duration, also the peak amplitudes of the spectrum. So there are different ways to process data and analyze data depending upon the nature of it. For transient signals, typical statistical analysis is not as important or not as useful as time domain analysis. for that kind of measurement exercise. We've got shock examples here, peak levels of 1G for a strong earthquake versus 3G for a sneeze, 100G for a karate chop to the head. These are measurements of the transient signals. So 300G for helmet testing. Gunfire projectiles can have peak G levels of up to 20,000 G. So our sensors that we're using for these different types of scenarios need to have levels that coincide, or dynamic ranges in fact that coincide with these different levels. And of course it can depend on where these sensors are based within the structure of interest. So for a car impact, for example, that will break human bones, it will be a larger value in the front of the car versus that would be measured in the passenger seat. This is a little bit of a furry picture, it's zoomed in quite a bit, but this is about time domain analysis versus frequency domain analysis. So you can see that peak displacement, so this is again about this aspect of displacement as a function of frequency. Okay, so you can see these levels. This is the mean threshold of human perception, which for higher frequencies has a lower vibration level than it is for a low frequency. And we will be able to measure that. We'll be able to observe some of these things in the laboratory exercise this week, where you can touch the vibrating structure and we can change the level of excitation, and so you can tell when it's possible to sense it with human perception. And then in terms of the vibration severity criteria, these lines come later. So if it's allowable, this is an acceptable level of velocity, vibration velocity around about 0.7 millimeters per second, versus 2 millimeters per second for a just tolerable machine. A machine that's got 5 millimeters per second or greater vibration level, then it would be in need of some predictive or some maintenance. We might specify acceptable vibration levels with different zones over different frequency range. For example, within these two frequency ranges, we might consider the levels here to be different for different reasons. There are various standards that are used for vibration testing. I'm just going to run through a couple of these very quickly. We've got ISO 2008-16 for machine vibration. The general guidelines are given within this part. For human exposure to vibration, we've got AS 2670. So this talks about people using equipment, sitting in vehicles, bus drivers, for example, truck drivers. The standards, the means of measuring exposure to whole body vibration, that includes accelerometers that might be mounted within the seat, pressure sensors, other types of transducers and measurement systems are all specified in these standards, and how to measure them as well as how to analyze these data. The general mounting of accelerometer standards, so some of the different mounting arrangements that I referred to, cement-based, stud-based, beeswax-based, these are specified within Australian Standard 2775. We've also got instrumentation for impact testing in road vehicles, ISO 6487. So this talks about where to mount accelerometers within a vehicle, how to analyze those data, how quickly to acquire the data, what type of frequency range we need to measure over, what sensitivity we need for the sensors, and so on. Torsional vibrations from internal combustion engines are given by AS Australian Standard 4594.5. So this will talk about, for example, transducers, torque transducers, encoders for making measurements of angle, tacho pulse train signals that are used to measure the shaft speed, and how to process the acceleration data that are measured, looking at things like condition monitoring aspects and so on. We're approaching the end of the presentation. Here are some examples of some measurements that have been done within the UTS facility, Faculty of Engineering and ID. So we've got a DVD duplication plant at Botany, looking at vibration from the road, making DVDs or duplicating DVDs, and clearly the vibration impacts the way that the head writes the data to the DVD. We also made some measurements of an electron microscope. There was vibration within the science building from the Thomas Street traffic, and so we needed to make measurements of the vibration to try to minimize how much vibration there was on the electron microscope and get better quality electron microscope measurements, and so on. Here's an example of a bike child testing seat testing experiment that was done in the dynamics labs. You can just about see the test seat over here, and there's some instrumentation connected to this bicycle, and we've got a ramp set up. You can see some triggering using these cables, and the accelerometer was mounted on the child, the seat, which is just not visible, directly above the rear wheel, and this was collected in a data acquisition system connected to the bike. And here is nature of some of the signals. So you can see acceleration as we go up the ramp, and then across the ramp the vibration dies, and then dropping off the ramp we've got lots of peak vibration level again. And so we're clearly interested to understand the impact of that vibration on the comfort and safety of the child. Another example, used for measuring whole body vibration, we've got different sensitivities. So there are weighting curves that are used to amplify or minimize the sensitivity or the importance of the frequencies at different frequencies within the frequency range, because as humans we're more susceptible to low frequencies than we are to high frequencies. So we've got different weightings that we apply, and they're specified in accordance with AS 2670.1. Here's another example of a vibration test study for a power station accident in Russia, and there's an explosion here, and you can see this was one of the largest hydroelectric power stations, 10 turbines, a significant piece of infrastructure, and this was the nature of the devastation that was caused when a turbine and rotor shed a blade and it became airborne. The turbine left the building and did significant amount of damage and lost a lot of human lives at the same time. The units were generating a significant amount of energy, so we can imagine there was a significant amount of energy involved. And this is the kind of catastrophic incident that is caused when rotating machinery isn't monitored properly, becomes damaged, misbalances occur, shaft whirl increases, a turbine blade catches a stator that's not moving and is ejected, and then the misbalance becomes more significant, and a catastrophic event such as this can occur. And there's some more slides within here, and that's the end of the presentation on applications of vibration signal analysis. I hope you enjoyed it. I look forward to seeing you in the labs during the course of the week, and I hope that you are able to have a good experience within those labs. Make sure that you review these lecture slides, review the video, and enjoy the rest of the course. Thank you.